Space is full of wonders. Among the most fascinating are neutron stars. These objects are incredibly dense and spin rapidly. They are remnants of massive stars. Studying neutron stars helps us understand the life and death of stars. Neutron stars are like cosmic laboratories. They allow us to study physics in extreme conditions. These conditions are impossible to recreate on Earth. Today, we'll explore the mysteries of neutron stars. So what is a neutron star? Imagine a star's core crushed to the size of a city. That's a neutron star. They are incredibly dense. A teaspoonful of neutron star material would weigh billions of tons. When a massive star nears the end of its life, it exhausts its hydrogen supply. It then starts fusing heavier elements, helium, carbon, oxygen, all the way to silicon and ultimately iron. This marks its red supergiant phase, where the star expands to hundreds or even thousands of times its original size. However, iron presents a problem. Fusing it does not release energy but instead absorbs it. Once a star can no longer generate energy through fusion, it loses the delicate balance between outward pressure and inward gravitational collapse. In mere seconds, the core succumbs to gravity, collapsing under its own weight. The intense pressure forces protons and electrons together. This creates neutrons. The resulting rapid contraction sends an immense shockwave outward. This triggers a spectacular supernova, a blast so powerful that for a brief moment the star may shine brighter than an entire galaxy. The fate of the core depends on the original mass of the star. If it's not massive enough to form a black hole, what remains is a neutron star, an incredibly dense, compact remnant packed with exotic matter and gravitational extremes. The formation of a neutron star is a dramatic event. Once formed, a neutron star is an object of incomprehensible density. The pressure is so immense that electrons are forced into protons, creating a sea of neutrons. Neutron stars exist under conditions so extreme that normal atomic structures cannot survive. Gravity on a neutron star is so strong that if standing on its surface were possible, you would weigh 1 trillion times more than on Earth. Light itself bends around the star due to gravitational lensing, meaning if you looked forward, you could theoretically see the back of your own head. At present, there are about 3,200 known neutron stars in the Milky Way. Neutron stars are mostly concentrated along the disk of the Milky Way. Some of the closest known neutron stars are about 400 light-years from Earth. Due to the extreme gravitational field surrounding a neutron star, time dilation is considerable. As a result, observers on Earth would experience 10 years, while only 8 years pass for those on the neutron star's surface, excluding the time distortion induced by the star's rapid rotation. Neutron stars are known for their extreme properties. As mentioned before, their density is astounding, but that's not all. They also have incredibly strong magnetic fields. Some neutron stars, particularly magnetars, possess magnetic fields up to 1 quadrillion times stronger than Earth's. These intense magnetic fields can have fascinating effects. They can cause the neutron star to emit beams of radiation. If these beams are pointed towards Earth, we see them as pulsars. Pulsars are like cosmic lighthouses blinking rapidly. Now we will delve into the fascinating world of stellar remnants, exploring the unique characteristics and differences between neutron stars, black holes, and white dwarfs. Neutron stars are not the only stellar remnants. These incredibly dense objects are formed when massive stars exhaust their nuclear fuel and undergo a supernova explosion. The core collapses under gravity, resulting in a neutron star. Other objects like black holes and white dwarfs also form when stars die. Black holes are born from the remnants of the most massive stars, while white dwarfs are the end state of less massive stars. Each of these remnants tells a different story about the life and death of stars. However, they differ in mass and properties. Neutron stars are incredibly dense, with a mass about 1.4 times that of the Sun, but packed into a sphere only about 20 kilometers in diameter. Black holes, on the other hand, can have masses ranging from a few times that of the Sun to billions of times more massive. Black holes are even denser than neutron stars. Their gravity is so intense that it warps space and time around them, creating a region from which nothing, not even light, can escape. This region is known as the event horizon. Their gravity is so strong that not even light can escape. This makes black holes invisible to direct observation, but we can detect them by observing the effects of their gravity on nearby stars and gas. White dwarfs, on the other hand, are less dense than neutron stars. They are the remnants of stars that were not massive enough to become neutron stars or black holes. These stars shed their outer layers, leaving behind a hot, dense core that cools and fades over time. They form when less massive stars die. The process involves the star expelling its outer layers, creating a beautiful planetary nebula, while the core contracts into a white dwarf. This remnant is about the size of Earth but contains a mass similar to that of the Sun. Unlike neutron stars, white dwarfs are not held up by neutron degeneracy pressure. Instead, they are supported by electron degeneracy pressure, a quantum mechanical effect that arises from the Pauli exclusion principle. This difference in pressure support leads to the distinct properties and behaviors of these stellar remnants. There are many fascinating subtypes of neutron stars. Pulsars, for instance, are rapidly rotating neutron stars. They emit beams of radiation from their magnetic poles. As they spin, these beams sweep across space like a cosmic lighthouse, creating pulses of radio waves, X-rays, or gamma rays. Magnetars are another intriguing type. They have even stronger magnetic fields than ordinary neutron stars. These fields can cause powerful bursts of energy. The study of these different types of neutron stars helps us understand the diversity of stellar remnants. One of the most awe-inspiring events is the merger of two neutron stars. When they collide, they create an explosion known as a kilonova, which synthesizes heavy elements such as gold and platinum. Incredibly, much of the gold on Earth may have originated from such an event billions of years ago. If you found this journey through neutron stars fascinating, don't forget to like this video, subscribe, and hit the notification bell for more deep dives into the wonders of the universe. Thanks for watching, and see you next time.